Okay, we have a goal programming question here. There's a company that produces 3 products: refrigerators, vacuum cleaners, and dishwashers. And we have, for each one of these products, we have the material cost per unit. We have the labor hour needed per unit of these products. We have the demand, the weekly demand for these products. And then we have the selling price per unit of each one of these products, as you can see here in the description of the question. We also know that the labor cost, each hour of labor costs the company $15 if it's within the normal production capacity of up to 8,000 hours. And for any extra labor hour, is like overtime, they have to pay $20 right here. And then there's a production budget of $150,000. That would be basically the cost that they can, the maximum cost that they can accept. And then, yeah, that's it. Selling price, everything. So let's go ahead and model this problem. We have 4 goals here. Goal 1, at least 200 refrigerators. So we have a goal on the amount of production, how many units to be produced. And then, of course, we have budget constraints and stuff like that. So for, okay, let's go ahead and we have to make sure that we address each one of those. So for the first one, this is demand. Okay, so the amount of production. First of all, let's figure out what are the decision variables here. Decision variables are the amount of production. That's what we want to determine here. If you look at the question here, formulate a goal programming model to determine the optimal mix of products to satisfy the various goals. So decision variables are the amount of production, and that would be for each one of these 3 products, the amount that is needed to be produced. Then decision, let me just change it to DVs, decision variables, production queues, production quantities. All right, for each one of these 3 products. And then for the goals, first one, the amount of production, we have a goal for that. Okay, so first off, we're gonna make sure that we're not going above, because here we see that there's a maximum. Actually, so if that's maximum, then we should be able to allow going under and over. So, but these guys also, the maximum demand, weekly demand should also be taken into consideration. So for here, the amount of production, let me actually go ahead and take each one of these, and that would be demand. Let's just put it here. So that would be demand goal, or production quantity goal, or yeah, but it involves demand. So production quantity. All right. So that is the first one. So variable of interest, variable for refrigerator, for vacuum cleaner. And I didn't put a title because we already have the titles here. And then for the dishwasher here. All right, let me also put the reference here. Okay, so that's the variable. That's the title of the goal here, or what we're trying to optimize here. Then we can do the positive and negative deviational variables. Consider those for each one of the production quantities. And then we have the LHS equal RHS, equal sign and RHS, which would be the goal. So for the LHS, always variable of interest plus negative deviational minus positive deviational. Here I have the formulas. And then the LHS is always the same, so I just drag it down. Equal sign always. RHS would be the target. So the target that we have, the goal that we have here is 200, 120, and 100 for dishwasher. Same level of importance. And I'm going to zoom out a little bit just so we have space here for writing the priorities. Okay. Yes, the variable of interest, the amount of production quantities. So those are the variables that we are defining the target for, the goal on them. And then positive, negative deviational variables, LHS and RHS. Now, our next step is to figure out what would be the bad deviation here. So when we say at least 200 refrigerators, we want to produce, so the goal, it's absolutely okay to go beyond, but we would like to avoid going under. So this is something that we do not appreciate based on the description of the goal here. So I'm going to change the color here to something different. Let's just go with that. So these are our bad deviations for priority 1. And then here it says same level of importance. So for priority 1, I just put so priority 1, I just put for what we are going to here. Let me just write objective. An objective here is sum or average of, doesn't really matter, of bad deviations on the first one. When you say take simple sum or simple average, it'll put same weights on them. But if we had different weights, we should have actually recorded the weights and then take a sum product. But right now, it'll work if we take a simple sum. All right. So that is it. Let me also make that. Okay. All right. So equal sign, equal targets, and then priority 1. That's what we want to have. And then value obtained, optimal value obtained. That is something to be determined later when we solve it. But for now, we're just going to move on to the next goal, because we have to formulate, we have to put everything first, put everything in the spreadsheet model before running the solver, before actually running the optimization, okay? So that's for goal 1. Goal 2, do not underutilize the production capacity of 8,000 labor hours. So what we want to avoid here is the amount of underutilization. We want to make sure that we use up the labor hour that we have available, the 8,000 hours. So I'm going to write down a production labor hour constraint just to measure the deviation from that, going under or going above, which would measure the amount of underutilization or overutilization of the production capacity of labor hours. And then we can define the second goal on the amount of underutilization. So this one actually is going to be production labor capacity, labor capacity. So that would be how the total number of hours, labor hours that we need for production of these quantities that are going to be determined by the solver later. So it's going to be some product of the decision variables and the labor hours per each one of them. So 20 times the amount of the number of refrigerators plus 12 times the number of vacuum cleaners plus 15 times the number of dishwashers. So that would be the total production labor hours. All right, so this is the formula, which it may actually go below. So then the decision variables, we allow this to be above or under, we allow the actual production capacity to go below or under the goal of 8,000. 8,000 is the normal capacity. And then the LHS is going to be always the same. Variable of interest plus negative minus positive deviational value. All right, so that's for production labor capacity. Now, for the second goal here, it says do not underutilize the production of production capacity, normal production capacity. So here is actually underutilization of capacity, production capacity. That's what we're trying to avoid. So underutilization would be negative deviational variable, negative deviation going under 8,000 on production capacity. That's what we want to avoid. And again, here, Control C, Control V. So just to, I'm just trying to copy the format, nothing else. And then LHS. LHS is the same, always. Variable of interest minus positive deviational plus negative deviational equal the target. The target for underutilization is 0. When it says do not do it or try to avoid it, so you don't, so the goal basically when it's not stated, that would be 0, right? When if you don't have a specific one, you try to avoid anything. So that would be 0, your goal. So that is going to define your priority 2. But here, which one of these 2 is going to be bad? Going over or going under? So definitely underutilization here, this is going to be a positive itself. So we already know that. And if it's positive, the only possible variable out of these 2 that can take positive value is going to be this one going above 0. So this is the bad deviation. This one definitely is going to be 0. So we don't even, we may even drop this, right? So it's not going to change anything. But this is a bad deviation. All right, let me write down the P2 now. P2 is going to be the bad deviation for second goal. All right. And the value obtained is to be determined later. Goal 3, profit level of at least $50,000. $50,000 profit level. Profit is sales minus material cost minus labor cost. Okay, so sales, I can write profit in 1 line, or I can actually make it in 3 lines, but I would probably write it in 1 line. So profit, that's the variable. So the variable is going to be sales. Sale is going to be some product of actually revenue, some product of quantities, and selling price. So that's revenue minus material cost. Material cost is going to be per unit. Again, some product of, and this is a direct cost, so depends on the actual quantity. Minus, now for the labor cost, as you can see here, the labor cost, the total labor needed is going to be DVs, some product of DVs and the labor per unit. But then the thing is, that is going to depend. If we're going under 8,000, it's going to cost us 15. And if we're going over, it's going to cost us 20. So that's why I would probably work with this constraint, because we have this sum product already taken care of and already calculated here. So I would actually work with this one. So it's going to be 15 times the production labor used under 8,000 or under, right? So that would be the production labor capacity, that would be the actual, minus any positive deviation. Okay, so if we're under 8,000, this is going to be definitely 0. So it's going to be the actual production, total production labor hour used, right? So K15 minus M15. If this is 0, it's going to be K15. And that happens if the K15 is 8,000 or less than 8,000, okay? Now, but it can also, but if it's positive, but if I mean, if D plus is positive, that means K15 is over 8,000. So over 8,000 minus whatever amount that is above 8,000, that'll make sure that this one, K15 minus M15, is going to stop at 8,000. All right. And then minus, there's going to be an additional cost, overtime cost, times the amount of overutilization, So that would be D plus for production labor capacity. All right. So Q4 15 times the actual amount of production, as long as it's below 8,000. But in order to make sure that it doesn't go above 8,000, the actual production capacity minus D plus, and then D plus itself, that would measure the amount that we're going over 8,000 multiplied by 20. All right, so that would be the formula for profit. And then again, profit definitely can have positive and negative deviations defined for that. All right, so LHS, same always. For RHS here, for goal 3, $50,000. That's the goal. Next, goal 4, production overtime should not exceed 1,000 hours. So first, before I move to that, let's define priority 3. So priority 3 is looking here, profit, it says again, at least 50,000. So going over is fine. Going under is not fine, right? So that's what we're trying to avoid. So I just highlight that as a bad deviation. Okay, so that's what we want to minimize. Okay, so P3 here for priority 3, what we want to minimize is going to be negative deviational on profit, going under the target of 50,000. So that's what we want to minimize. And then of course, that'll be that defines our third priority in the list of goals that we have. Lastly, goal 4 is going to be production over time should not exceed 1,000 hours. Production over time. So over time, we wanna limit that to 1,000 hours. So overtime is going to be measured by D plus, the amount of overtime going above 8,000 production labor capacity. Anything above 8,000, that would be considered the amount of overtime. So overtime is the variable of interest. All right. And the target here, and again, I'm going to allow both of these. But then what we want to minimize is going to be like the amount that you exceed 1,000. So the negative is going to be positive. So it's going to be similar to this. So we wanted to avoid underutilization. Here, we want to also avoid overtime, but we have a specific target for that of 1,000. Everything else remains the same. P4 is going to be bad deviation on overtime. And yeah. All right. So we managed to take care of all the goals that we had, but we also need to make sure that we captured all the realities in the question, and every single facts that is mentioned and is going to actually restrict the production capability, right? In this case, because this is a production planning question, you want to make sure that if there's any other limit stated in the question is also taken into consideration. So let's take a look. So we took care of the labor cost. It actually was reflected in the profit function. There's actually one production budget that we need to make sure that is taken care of. Selling price, we took care of that. Demand, yes. Labor hour, yes. Material cost, also in the cost function. Cost function, capacity, overtime, underutilization of production capacity, everything. The only thing is the production budget. So I just need to write that as a hard constraint because there's nothing, there's no even not a possibility of going over this one. So that'll be a hard constraint. You can define it in the same format, but then you need to make sure that you do not define, you don't even allow the possibility of D plus being positive. So let's just do that, or you can actually define it as an operational constraint. But let's just do that. Production budget, and then the variable is going to be, so here is going to be, so in the profit function, everything that is related to the cost, that'll measure the amount of money that you have to spend on production. That would be your labor cost plus normal labor cost plus overtime cost, 20 times the amount that you go over 8,000 plus 15 times the production labor used, anything up to 8,000 here, plus the material cost. So that we want to make sure that stays. And by the way, this is going to be, you allow this to be, to go under 150,000, but you do not allow it to go above by not even defining a positive, by even not considering a possibility of having a positive deviational variable for that. So that'll be taken care of automatically. All right. So let me take the left-hand side and the formula and everything. So it seems that we're all set and we took care of all the other constraints. So let's go ahead and solve this. So data tab, solver. So for first priority, we want to minimize bad deviation for priority one, for the first goal. All the decision variables, all the highlighted cells should be given here. So these three main decision variables, comma, everything else, comma, and this. All right, all the highlighted cells. And then the constraints. So the constraints are going to be, I mean, and since we defined it in this format, in the format of goal constraint, all we need to do is to put all the goal constraints, LHS, for all of them equal the goals RHS. Okay. So priority one, and then this is a goal programming. We have multiple priorities, multiple goals. So we're going to try with priority one, and then we go step by step. All right, solve. Okay, let's take a look. Okay, so with the amount of, this is priority one, so this is the objective. Let's take a look here. So decision variables, 120, that was the goal, 100. So vacuum cleaner and dishwasher is satisfied. For refrigerator, we're a little under, we're a little short, right? And I'm actually, I didn't impose the integer constraint, we can actually do that. Let's just go back to the solver and try to do it again. But this time I'm gonna make sure that the values that we get here are going to be integer for the decision variable. Okay. So 73, 120, and 100. So the goals for vacuum cleaner and dishwasher are satisfied. Refrigerators were short 127 units. But then production capacity, we're going under. As you can see here, what is making this, so because we have a hard constraint here, the production budget, yes, production budget of 150, that's the main restrictive factor here, as you can see here, because we had, I mean, we're not even getting close to the amount of production capacity that is available, right? But then the reason for that is because we have another very hard constraint of production budget. So that's fine. I mean, 125, 127 is going to be the value obtained for P1. So let's try. Let's go back to solver. So we're going to update the objective function to the second one, to second priority. But we need to add the optimal value of the first priority at its optimal level. Okay, so let's just solve it again for second priority and see if we can go a little under. So a little under, little improvement, 3585. Okay. And then, yeah, so we keep that at that level, data tab, again, solver. Priority 4 is already achieved, but it's very important to make sure that priority 3 is considered before. So I'm going to update that again to priority 3 this time. And by adding the second priority, since we, yeah, that's okay. Since we added the integer constraint and the answers are not necessarily at the corner, it may make sense actually to also consider less than or equal. But just to follow our procedure, I'm going to go with equal sign. Okay, so let's solve again. 94, 0, 15. And then priority 4 is already optimized at 0 level. So we're not actually doing any overtime. So that is it. So this is basically what we found. We're going 1 unit above on this one. And that, again, that's because we are using the integer and the answers are not necessarily at the corners. But that's okay. I mean, we're allowed to go over 100 units. That was the minimum requirement, but it can go all the way to 240. All right, so that's for this one.